10,
CLS go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition, liftoff of Space Shuttle Discovery, taking the space station to full power.
Every civilization, from the first humans who gazed up at the night sky to the modern physicists peering through their telescopes, has asked the same question: how far can we go? So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. It is a question that humbles us, terrifies us, and yet refuses to release its grip on the human mind. The moon was once unthinkable. Mars was once unreachable. Even the idea of leaving the Earth at all was once considered an act of madness reserved for dreamers and fools. But light, the silent messenger of the universe, has always stood apart. It crosses the void with perfect obedience to the laws of reality, arriving from distant stars long dead, carrying stories billions of years old. In its unchanging speed, light taunts humanity with a truth we cannot escape. There is a limit, a cosmic boundary written into the fabric of existence itself. And yet, we dream. Long before engines roared or equations were written, before metal pierced the sky or radios spoke across continents, there were only humans and darkness. Fires flickered in caves. The world ended at the edge of the trees. And above it all hung the sky, vast, cold, unreachable. The stars did not simply decorate the night, they ruled it. They were gods, ancestors, omens, and maps. To look upward was not curiosity, it was survival. The stars told hunters when to move, farmers when to plant, sailors where they were. But they also did something far more dangerous. They suggested that the world did not end where our footsteps stopped. They whispered that reality extended far beyond the horizon, and that we were small within it. That whisper never went away. Every major leap in human history carries the same underlying impulse, the refusal to accept boundaries. When the oceans seemed endless and lethal, we crossed them anyway. When mountains blocked the land, we carved paths through them. When the sky itself seemed forbidden, we built wings and dared gravity to stop us. Space travel is not an anomaly in human behavior. It is its purest expression. To understand how far we can travel through space right now, we must first understand why we are compelled to try at all. Because the answer is not technological. It is psychological. It is evolutionary. It is written into us. Our ancestors who wondered what lay beyond the hill survived. Those who did not, vanished. Curiosity was never a luxury. It was a weapon. The moment humans stood upright, the horizon became a challenge. Every unknown represented both danger and opportunity. Food, shelter, rivals, allies, all hidden just beyond sight. To remain still was to risk extinction. Movement meant knowledge. Knowledge meant control. And so, humanity became a species defined not by strength or speed, but by restlessness. That restlessness did not disappear when the Earth was mapped. When the last white spaces vanished from globes, when satellites photographed every inch of land, something unsettling occurred. For the first time in history, there was nowhere left to go. At least, not on Earth. And the sky was still there. Space is not simply the next frontier, it is the only frontier left. A final unknown vast enough to absorb humanity's oldest hunger. But space is different. Oceans push back. Mountains resist. Space does not care. It does not push back. It simply waits, indifferent, lethal, and silent. There is no air to scream through, no surface to stand on, no mercy for mistakes. And still, we reach for it. Because deep down, humanity understands something terrifying. Staying confined to one world is not safety, it is fragility. Every extinction event written into Earth's history shares a common lesson. Planets are not permanent sanctuaries. Asteroids fall, climates shift, supervolcanoes awaken, stars change. Survival favors those who spread out, not those who huddle in one place and hope for mercy. Space travel, at its core, is not about exploration. It is about survival. But survival alone does not explain the poetry we attach to the stars. It does not explain why children instinctively draw rockets, why civilizations align monuments to the heavens, why the idea of leaving Earth evokes awe instead of terror. There is something else, something almost spiritual, pulling us outward. The night sky is a mirror. When we look into it, we do not just see distance, we see time. Every star is a ghost. Its light began its journey long before we existed. Some of the stars we see no longer exist at all. We are witnessing the past, layered upon the present, stretched across incomprehensible scales. To look into space is to confront our mortality, and paradoxically, to defy it. If the universe is vast and ancient, then meaning cannot be handed to us. It must be created. Exploration becomes a declaration. We were here. We reached. We learned. We refuse to remain silent observers in a universe that does not acknowledge us. That is why spaceflight matters in ways numbers cannot capture. It is not about how far we have gone, but about what it says that we tried. When the first humans broke free of Earth's gravity, they did not just escape the planet. They crossed an invisible psychological barrier. For the first time in history, humanity was no longer bound entirely to a single world. The sky was no longer a ceiling. It became a doorway, but that doorway was narrow. Gravity is not merely a force, it is a gatekeeper. Earth holds onto us with relentless insistence. To leave requires immense energy, precision, and sacrifice. Every kilogram of mass must be fought for. Every second beyond the atmosphere demands technology functioning at the edge of failure. Space travel does not forgive romanticism. The universe operates on scales hostile to biology. Temperatures swing violently. Radiation scours unprotected flesh. Time itself becomes distorted as speed increases. The farther we travel, the more reality asserts its rules. And this is where the dream collides with the present. Because when we ask, how far can we travel through space right now? We are not asking about desire. We are asking about limits. And limits define our era as much as our ambitions. Human beings today are capable of leaving Earth, but only briefly. We can orbit our planet. We can visit its nearest neighbor. We can send machines far beyond our reach, but we cannot follow them. Not yet. The distance between what we can imagine and what we can endure remains vast. Our bodies evolved for a narrow band of conditions: gravity, atmosphere, magnetic shielding. Space strips those away instantly. Muscles weaken, bones lose density, vision degrades, cells accumulate damage. The human body, magnificent as it is, was not built for the void, and yet we persist in trying to adapt it. This tension between aspiration and limitation defines modern space exploration. We are a species caught between epochs, too advanced to be satisfied with Earth alone, too fragile to roam the stars freely. It is an uncomfortable position, a transitional one. We stand at the shoreline of the cosmic ocean, staring out with ships that are barely seaworthy, knowing that something immense waits beyond, and that we are not yet ready. But readiness has never stopped us before. Every great journey in human history began before we were truly prepared. We crossed oceans without knowing what lay on the other side. We ventured into deserts without maps. We climbed mountains without understanding altitude sickness. Preparation has always followed curiosity, not the other way around. Space is no different. The question is not whether humanity wants to travel farther. That desire is undeniable. The real question is whether reality will allow it, and at what cost. As we move deeper into this exploration, we must confront uncomfortable truths. Distance in space is not measured in kilometers. It is measured in time. It is measured in lifespans. It is measured in patience. Even our nearest cosmic neighbors exist on scales that mock intuition. The moon, close enough to touch with our eyes, is still days away. Mars, the red beacon of ambition, is months away, and only reachable during narrow windows dictated by celestial mechanics. Beyond that, the solar system stretches outward into a realm where years become decades, and decades become lifetimes. And beyond the solar system, stars are not destinations, they are generations away. To ask how far we can travel right now is to confront the uncomfortable reality that the universe is not built for quick journeys. It is built for endurance, or not at all. Yet this has never extinguished the dream. If anything, it sharpens it, because every limitation forces a choice. Do we accept the boundary, or do we attempt to rewrite it? Throughout history, humanity has chosen the latter, sometimes successfully, sometimes catastrophically, but always relentlessly. Space travel sits at that same crossroads. In this series, we will strip away fantasy and confront reality. We will examine what human beings can actually do, not someday, not theoretically, but right now. We will trace the hard edges of technology, biology, and physics. We will follow our machines where our bodies cannot yet go, and we will stare honestly at the silence that lies beyond our reach. Not to diminish the dream, but to understand it, because only by knowing our limits can we hope to push them. And somewhere beyond the atmosphere, beyond the fragile shell of air that protects us, the universe waits, unmoved by our hopes, untouched by our fears, indifferent to our timelines. The question remains, as it always has, how far can we go? And perhaps more importantly, how far are we willing to become something new in order to find out? Distance is a familiar thing on Earth. It is measured in footsteps, in hours of travel, in the slow fatigue of muscles, and the passing of landscapes through windows. Distance feels intuitive. It can be conquered with effort. Given enough time, almost any place on Earth can be reached. Space shatters that intuition. In space, distance is not an inconvenience. It is a fundamental barrier. It is not merely far. It is far in a way the human mind did not evolve to understand. Numbers lose their meaning. Comparisons collapse. Language itself begins to fail. And this is the first truth we must confront when asking how far we can travel through space right now. We do not truly grasp how far space is. The universe does not scale gently. It explodes outward, abandoning human proportions almost immediately. The moment we leave Earth, familiar distances vanish. The planet itself shrinks to a fragile marble. The moon, so dominant in our night sky, becomes a distant companion floating hundreds of thousands of kilometers away. And this is still our cosmic backyard. Beyond that, the solar system opens like an abyss. Planets are not neighbors. They are islands separated by emptiness so vast that light itself takes minutes to cross it. Even at extraordinary speed, travel between them is slow, methodical, and unforgiving. There are no shortcuts, no highways, only trajectories carved by gravity and patience. On Earth, speed solves distance. In space, speed collides with physics, because speed has a ruler, and that ruler is light. Light does not feel fast to us, it feels instantaneous. Flip a switch, and the room is bright. Look at the sun, and warmth arrives without delay. But this is an illusion born of scale. Light is unimaginably fast, so fast that it shapes reality itself. Nothing with mass can reach its speed. This is not a technological limitation. It is not a failure of engineering. It is a property of the universe. Light travels at roughly 300,000 kilometers per second. That number is not impressive until you understand what it implies. At that speed, light can circle Earth more than 7 times in a single second. It can reach the moon in just over a second, the sun in about 8 minutes. And yet, in cosmic terms, light is slow. The nearest star beyond our sun is so distant that its light takes more than 4 years to arrive. 4 years, traveling at the fastest speed reality allows, just to cross the gap to the closest stellar neighbor. This is the scale we are dealing with. When astronomers speak of distance, they abandon kilometers almost immediately. They speak in light years, not as a poetic flourish, but out of necessity. A light year is not time. It is distance, how far light travels in 1 year. And even that unit quickly becomes inadequate. The Milky Way galaxy is roughly 100,000 light-years across, 100,000 years of light-speed travel from one side to the other. Our galaxy alone contains hundreds of billions of stars, and beyond it, trillions of galaxies stretch into darkness. Space does not merely dwarf human travel, it mocks it. This is why the question, how far can we travel, cannot be answered without confronting speed and the brutal constraints that govern it. On Earth, increasing speed feels linear. Faster engines, shorter travel times. But in space, speed demands energy, and energy demands mass. And mass demands more energy to move. This feedback loop becomes merciless. To go twice as fast requires far more than twice the energy. To approach even a fraction of light speed requires energies that border on the absurd. The closer you get, the more reality pushes back, demanding infinite energy for the final step, a step that can never be taken. Light speed is not a wall we can crash through. It is an asymptote, something we can approach forever without touching. This alone defines how far we can go right now. Our fastest human-made spacecraft move at speeds that feel extraordinary by Earth standards. Tens of thousands of kilometers per hour, enough to leave Earth entirely, enough to escape the sun's grip, enough to drift into interstellar space. And yet, at those speeds, the stars remain effectively unreachable. Even traveling tens of thousands of kilometers per hour, it would take tens of thousands of years to reach the nearest star. This is the second truth of space travel. Distance scales faster than speed can compensate. But speed is not the only tyrant here. Time itself becomes an adversary. In space, time is not a background detail. It is the currency of travel. Every journey is a negotiation with mortality. Months become years, years become lifetimes, and lifetimes are not negotiable. Human beings are not machines that can be powered down and restarted centuries later. We age, we weaken, we change, we die. A journey measured in decades is not merely long, it is generational. It demands children born in transit, lives lived entirely between stars, destinations reached by descendants who did not choose the journey. This transforms travel into something closer to migration, or exile, and even then, biology rebels. Long exposure to radiation damages DNA. Microgravity reshapes the body. Isolation fractures the mind. Space does not kill instantly. It erodes, slowly, quietly, relentlessly. This is why, despite our dreams, human space travel remains tightly bound to proximity. Low Earth orbit, the Moon. Short durations measured in months, not decades. Distance is not just how far you must go. It is how long you must endure being unprotected. But even if we could overcome biology, speed itself carries a hidden cost. At high velocities, space becomes hostile in new ways. Dust particles, harmless at low speed, become bullets. At a significant fraction of light speed, even individual atoms strike with devastating energy. The universe is not empty, it is sparse, but not vacant. And at extreme speeds, sparseness is enough to kill. This is the cosmic irony. The faster you go, the more dangerous space becomes. So the universe traps us in a delicate balance. Too slow, and distance defeats us. Too fast, and physics turns lethal. Some imagine that technology alone will bridge this gap, that better engines, stronger materials, smarter systems will eventually render distance irrelevant. But physics does not negotiate. It allows clever workarounds, not exceptions. We can exploit gravity to steal momentum. We can coast efficiently instead of burning fuel constantly. We can send machines instead of bodies. We can stretch lifespans, shield against radiation, simulate gravity, sleep through years. But none of these erase the fundamental truth. The universe is vast because it is allowed to be. Distance is not a flaw. It is a feature. It prevents collapse. It isolates catastrophes. It ensures that events unfold locally rather than universally. The same distances that frustrate our exploration also protect us from cosmic disasters happening elsewhere. To travel far is to fight the architecture of existence itself. And yet, we persist. Because while the universe does not care if we travel it, it does not forbid it either. It merely sets the price. And that price is time, energy, and transformation. When we speak of current space travel, we must separate three kinds of distance: communication distance, robotic distance, and human distance. Light allows us to communicate across staggering scales. Signals cross the solar system in hours. Images from the edge of interstellar space still reach Earth. In this sense, our awareness extends far beyond our bodies. Machines extend us farther still. They do not age. They do not fear isolation. They do not need air or gravity. They can drift for decades, centuries, even millennia. Robotic probes are humanity's long fingers, reaching into regions we cannot touch. But human distance remains stubbornly small. We are creatures of warmth and pressure and rhythm. Our bodies expect sunrise and sunset, gravity and sleep, social contact and sensory variation. Space offers none of these naturally. To survive, we must carry Earth with us, or remake ourselves. This is why the question of distance becomes philosophical as much as technical. How far we can travel depends on how much of ourselves we are willing to change. Are we willing to alter biology, to merge with machines, to live without planets, to redefine what it means to be human? Distance forces these questions upon us, because the universe will not meet us halfway. Even within our own solar system, distances stretch patience thin. Travel times are measured in months and years. Communication delays grow noticeable. Real-time conversation disappears. Autonomy becomes mandatory. Beyond the solar system, delay becomes silence. Messages take years, then decades, then centuries. The concept of response dissolves. A civilization that sends humans to the stars must accept that those humans are no longer participants in the society that launched them. They become something else. Seeds flung into darkness. This is not a technical problem. It is a cultural one. It asks whether humanity is prepared to fracture across time and space, to exist as separate branches that may never speak again. Distance does not just separate locations, it separates histories. And this is the final cruelty of cosmic scale. The farther you go, the less you share. Shared language erodes. Shared values diverge. Shared memory fades. Distance becomes identity. So when we ask how far we can travel through space right now, we are really asking, how much separation can we tolerate? At present, the answer is clear. We tolerate very little. We cling to Earth. We orbit it. We venture briefly beyond it. We send machines where we cannot follow, and we dream, endlessly, of closing distances that physics insists on keeping open. But dreams are not meaningless. They shape preparation. Every calculation, every engine test, every long-duration mission is a negotiation with distance, a lesson learned in patience, a step toward endurance. We are learning how to exist without immediacy, how to operate with delay, how to survive without gravity, how to endure confinement, how to repair ourselves far from home. These are not glamorous achievements. They do not feel like conquest, but they are foundational, because the universe will not be rushed. Distance is not an enemy to defeat. It is a reality to adapt to. And adaptation has always been humanity's greatest strength. The first step into space did not begin with a rocket. It began with a realization, quiet, unsettling, and irreversible. Earth is not the center of anything. For most of human history, the sky revolved around us. The sun rose and set for our benefit. The stars wheeled overhead like ornaments. Even when we learned the truth, that Earth moved, that it circled, that it was one body among many. The knowledge remained abstract, numbers on parchment, diagrams in books. It was not until we left Earth that the truth became undeniable. When the first humans slipped beyond the atmosphere, there was no thunderclap of enlightenment, no divine revelation. There was only a fragile sphere hanging in blackness, thin-skinned, luminous, alone. And suddenly, everything changed. Spaceflight did not merely expand humanity's reach, it redefined humanity's place. Before we can understand how far we can travel right now, we must confront how tentative our first steps truly were, and how close we came to never taking them at all. The early days of space exploration were not driven by curiosity alone. They were driven by fear. Fear of falling behind. Fear of vulnerability. Fear that whoever controlled space would control Earth. The Cold War transformed the sky into a battlefield before humanity had even learned how to survive there. Rockets were built not to explore, but to threaten. Spaceflight was a byproduct of weapons capable of crossing continents. And yet, something unexpected happened. The same machines designed for annihilation opened a door to transcendence. When the first satellites reached orbit, they did not conquer territory. They revealed perspective. Weather systems spanning continents. Borders rendered meaningless. A planet operating as a single interconnected system. Still, orbit was not enough. Orbit is not freedom. It is captivity in motion. You are always falling, and always missing the ground. The Earth never releases you completely. To truly leave, you must break free, and that required an act of audacity bordering on insanity. The Moon had watched humanity since before history began. It governed tides, marked time, haunted myths. It felt close, close enough to touch, but it was not. It was 250,000 miles away, separated by vacuum, radiation, and silence. To reach it required energy, never before concentrated into a single machine. It required precision beyond precedent. It required humans to entrust their lives to stacks of fuel controlled by equations and hope. The Saturn V rocket was not elegant. It was brutal. A tower of controlled explosions, burning thousands of tons of propellant in minutes, tearing itself away from Earth by sheer force. When it launched, the ground shook, buildings rattled. The sound was not thunder, it was the planet protesting. And then, impossibly, the rocket climbed. The Moon missions were not smooth triumphs. They were fragile sequences of events that tolerated no mistakes. Every phase, launch, orbit, trans-lunar injection, descent, ascent, rendezvous, re-entry, balanced on the edge of catastrophe. There was no rescue, no backup, no second chance. The astronauts knew this. They flew anyway. When humans first set foot on the Moon during Apollo 11, it was not the footprint that mattered. It was the pause, the silence, the moment of stillness before movement resumed. Because in that moment, humanity became something it had never been before. Multiplanetary. But the triumph hid a harsher truth. The Moon is close, cosmically speaking. Light reaches it in just over a second. Radio signals arrive almost instantly. Travel takes days, not years. And even so, it pushed us to the limit. The lunar surface was not welcoming. It was hostile in subtle ways. Dust that clung to everything. Temperature extremes that defied comfort. Radiation unfiltered by atmosphere. A horizon unnervingly near. The Moon did not feel like a destination. It felt like an outpost. Temporary, fragile, borrowed. The mission succeeded not because the Moon was easy, but because it was barely possible. And when the political urgency faded, so did the will to return. This is a pattern worth examining. Human space travel advances not in a smooth arc, but in bursts, driven by urgency, constrained by cost, and limited by endurance. After the Moon landings, humanity did not surge outward, it pulled inward. We learned something important. Reaching somewhere once is not the same as being able to stay. The moon taught us that distance alone does not define travel. Sustainability does. To live beyond Earth requires more than engines. It requires systems for air, water, food, waste, health, and sanity, all functioning without fail, far from immediate help. And this realization redirected human spaceflight inward, closer to home. Instead of racing farther, we learned to stay longer. Low Earth orbit became our laboratory. Here, humanity built a fragile bridge between Earth and space. A place where gravity loosens its grip but does not vanish, where resupply remains possible, where emergencies can still be survived. This bridge took many forms, but it reached its most complex expression in the International Space Station. The ISS is not a ship. It does not travel to destinations. It circles endlessly, bound to Earth, moving fast enough to stay aloft, but not free enough to leave. And yet, it represents one of the most important milestones in space exploration. For the first time, humans lived continuously off Earth for months, then years. They slept while floating. They ate recycled water. They exercised to keep bones from dissolving. They looked down and watched continents pass beneath them in silence. Orbit stripped away romance. It replaced it with routine. And routine is where reality reveals itself. In orbit, the body begins to change almost immediately. Muscles weaken without resistance. Bones shed calcium. Fluids shift upward, altering vision. The immune system behaves unpredictably. Space does not kill you quickly. It unravels you slowly. Psychologically, the effect is just as profound. Isolation compresses time. Confinement magnifies tension. Earth becomes both distant and omnipresent, always visible, never reachable. Astronauts describe a strange duality, feeling both insignificant and deeply connected. Borders vanish, conflicts feel absurd. The planet appears fragile, finite, irreplaceable. This cognitive shift, sometimes called the overview effect, may be one of space travel's most enduring legacies. But it also underscores a limitation. We have learned how to survive in space. We have not learned how to thrive there. The ISS exists because Earth supports it. Supplies arrive regularly. Crews rotate. Experiments end. Emergencies have contingencies. Remove Earth from the equation, and the entire system collapses. This is the boundary of human travel right now. We can leave Earth, but we cannot escape dependence on it. Even the moon missions were temporary intrusions. Flags planted, samples collected, footprints left, and then retreat. No cities, no permanent presence, no continuity. Our first steps beyond Earth were courageous, but they were also cautious. Every mission was designed with an exit strategy. Every journey assumed a return. We have not yet accepted the idea of irreversible distance. Machines have. Robotic probes do not return. They cross boundaries without expectation of rescue. They drift until power fades, then continue silently. Humans do not yet accept that fate for themselves. And perhaps that is wise, because the cost of error increases exponentially with distance. In orbit, rescue is possible. At the moon, it is unlikely but conceivable. Beyond that, it becomes fantasy. The early steps into space taught us humility. They revealed how unforgiving the environment truly is. They showed us that courage alone does not conquer physics. They also taught us something else, something quietly profound. Space does not reward speed. It rewards preparation. The moon landings were not rushed improvisations. They were the result of years of testing, failure, redesign, and repetition. Countless simulations, endless checklists, painful lessons learned from disasters narrowly avoided, and some not avoided at all. Every success rested on a foundation of restraint. This is why, decades later, humanity has not leapt dramatically farther, not because we lack ambition, but because we understand the cost of recklessness. The first steps beyond Earth revealed the difference between possibility and sustainability, between reaching and remaining. And that distinction defines how far we can travel right now. we stand at a threshold similar to the one faced by early ocean explorers, capable of coastal voyages, uncertain of crossing vast open seas, aware that beyond the horizon lies opportunity and oblivion. The Moon and low Earth orbit are our coastlines, familiar enough to navigate, dangerous enough to command respect. Beyond them lies deep space, not yet a destination, but a question. When the human body reached its limits, humanity did not stop. It adapted. If flesh could not endure the cold silence beyond Earth's neighborhood, then something else would go in our place. Something that did not need air. Something that did not fear isolation. Something that could drift for decades without complaint. This is how humanity learned to travel farther than it ever physically could. Not with footsteps, but with machines. Robotic explorers are not merely tools. They are extensions of human intent, our eyes, our hands, our curiosity, projected outward into regions we will not see in our lifetimes. They carry no dreams of return. They are launched knowing they will die alone, far from home, long after their creators are gone. And yet, they keep going. If you want to know how far humanity can travel through space right now, do not look at where humans are. Look at where our machines are still moving. The most distant travelers ever built were never meant to be heroes. They were designed as instruments, precise, limited, fragile. Their mission timelines were measured in years. Their power sources were expected to fade. Their destinations were never fully understood. And still, they crossed boundaries no human has even approached. The story of robotic exploration begins modestly. Early probes barely escaped Earth's gravity. They sputtered into orbit, failed silently, burned up, or drifted uselessly. Each failure taught engineers a harsh lesson. Space does not forgive optimism, but failure also refined resilience. Gradually, humanity learned how to build machines that could survive vacuum, radiation, extreme cold, and unimaginable distance. Solar panels unfolded, antennas locked onto Earth like lifelines. Instruments listened patiently for whispers from places light barely touched. Then came a daring idea. What if we didn't just visit nearby planets? What if we sent something that would never come back? In the late 1970s, humanity launched 2 machines on trajectories that would carry them beyond every planet, beyond the sun's influence, and eventually into the space between stars. They were named Voyager 1 and Voyager 2. At the time, no one could guarantee they would survive their first encounters, let alone decades of travel. Their computers were weaker than modern calculators, their memory measured in kilobytes. Their entire existence depended on a steady decay of radioactive material, generating just enough electricity to keep them alive. They were not built to last forever, but the universe allowed them to. The Voyagers were flung outward using a rare cosmic alignment, a gravitational choreography that occurs only once every 176 years. By slingshotting around the giant planets, they stole momentum, accelerating without burning fuel. This was not speed in the human sense. It was patience rewarded. As Voyager 2 passed Jupiter, Saturn, Uranus, and Neptune, it revealed worlds no human had ever imagined. Storms larger than Earth, rings intricate and fragile, moons cracked open, leaking oceans beneath ice. Voyager 1 took a different path, one that would send it out of the plane of the solar system entirely. And then, something profound happened. As Voyager 1 turned its camera back toward home for the last time, Earth appeared as a single pixel suspended in a beam of sunlight. That image, later known as the pale blue dot, changed how humanity saw itself. Every war, every love story, every belief system, every child who ever lived, all of it contained within a speck. Voyager 1 was not just traveling through space, it was reframing meaning. Then, slowly, almost imperceptibly, the sun's influence began to fade. Solar wind weakened. The protective bubble of charged particles that defines our star's domain thinned. And one day, Voyager crossed a boundary no human had ever crossed. It entered interstellar space, not a dramatic frontier, not a glowing border, just a quiet shift in pressure and particles. The heliopause, the edge where the sun's dominance ends and the galaxy begins. Voyager 1 is now farther from Earth than any object humanity has ever made. Its signals take more than a day to arrive. Its power dwindles. One by one, instruments are shut down to preserve its fading heartbeat. But it is still alive, still speaking, still moving, and it will continue long after its voice falls silent. This is what robotic travel allows: time without urgency, distance without endurance. Machines do not experience loneliness. They do not measure years in aging bodies. They do not mourn what they leave behind. They simply continue. And the Voyagers are not alone. Before them came the Pioneer probes, earlier, simpler travelers that first hinted at the scale of escape velocity. They were the first to feel the sun's grip loosen permanently. After them came a new generation. New Horizons was not designed to leave the solar system initially. It was designed to do something simpler, to reach Pluto. Even that goal required a journey of nearly a decade. When New Horizons finally arrived, it did not enter orbit. It could not slow down enough. It screamed past at incredible speed, gathering data in a brief window before continuing outward. Pluto was not a destination. It was a waypoint. This is the pattern of robotic exploration. Flybys, not settlements. Glimpses, not stays. Because slowing down costs energy, and energy is precious. Every robotic mission makes a choice. Spend fuel to stop, or spend time to go farther. Human missions always choose stopping. Robots choose distance, and distance reveals scale. Beyond the planets lies a region almost entirely empty. The Kuiper Belt, scattered remnants of planetary formation, drifting silently. Beyond that, the hypothesized Oort cloud, a vast spherical shell of icy debris extending perhaps a light year from the sun. Even here, humanity has not sent a dedicated explorer. And yet, our probes will eventually pass through it, not by design, but by inevitability. This is the strange truth of robotic travel. Once launched, there is no turning back. Every second increases distance. Every course correction is minor compared to the momentum already gained. Robotic probes are arrows shot into darkness. They do not aim for destinations so much as trajectories, and the farther they go, the more they teach us a difficult lesson. Distance erases control. Commands take hours, then days, then weeks. Eventually, they take years. At that point, a probe becomes autonomous by necessity. It must decide how to respond to failure, when to conserve power, how to orient itself. This autonomy is a rehearsal, not for machines, for humans. Because any future human journey beyond the solar system will face the same silence, the same delay, the same absence of immediate guidance. Robots are our test subjects. They reveal what breaks first. Electronics degrade, power fades, memory corrupts, instruments fail, but systems designed with redundancy endure. The Voyagers were never meant to last this long. They lasted because their designers assumed failure and planned around it. This philosophy, designing for decay, may be the most important lesson robots teach us. Space travel is not about perfection. It is about graceful failure. Every robotic mission ends the same way, not with destruction, but with quiet fading. A final signal, a last transmission, and then nothing. The probe does not explode. It does not crash. It simply becomes another cold artifact drifting among stars. In this sense, robotic explorers are immortal in a way humans cannot be. They may outlast civilizations. They may pass near other stars millions of years from now. They may become the only evidence that we existed at all. The Voyagers even carry messages, encoded sounds and images of Earth, not as communication, but as gesture. A time capsule hurled into eternity. This reveals something intimate about humanity. We do not send machines merely to learn, we send them to be remembered. And yet, for all their reach, Robots expose the boundary of our present capability. They can go far, but they cannot carry us with them. They do not solve the problem of human travel. They postpone it. They map it. They warn us. Every kilometer they travel underscores the disparity between mechanical endurance and biological fragility. We can send probes beyond the solar system. We cannot follow. Not now. Not with bodies that break. Not with lifespans measured in decades. Robotic travel answers one version of the question: how far humanity's influence can reach. But it leaves unanswered the harder question: how far humans themselves can go. And that question returns us inward, closer to home, where bodies still matter, gravity still pulls, and the limits of endurance define reality. For all our dreams of distant worlds, for all the probes drifting beyond the sun's reach, humanity's physical presence in space remains astonishingly close to home. Not the moon, not Mars, not the vast emptiness between the stars. Just above us. A thin shell of space no farther away than the width of a continent. Low Earth orbit. This narrow band, stretching only a few hundred kilometers above the surface, is the farthest human beings can reliably travel right now, stay alive, and return from. It is both a triumph and a confession, proof of our ingenuity and a reminder of our fragility. To understand how far humans can travel today, we must abandon the romance of rockets and confront the lived reality of orbit, not as spectacle, but as habitat. Low Earth orbit is not deep space. It is not freedom from Earth. It is a delicate compromise between escape and dependence. Astronauts aboard the International Space Station are not explorers in the traditional sense. They do not venture outward. They circle endlessly, locked into a gravitational embrace they cannot break without extraordinary effort. At roughly 400 kilometers above Earth, the ISS completes one orbit every 90 minutes. Day, night, day, night. 16 sunrises and sunsets every 24 hours. Time fractures. The body struggles to anchor itself to rhythm. From a distance, the station looks heroic, a cathedral of metal gliding against the black. Up close, it is cramped, loud, and relentlessly mechanical. Air circulates constantly. Fans hum. Pumps vibrate. Silence does not exist. This is not a place built for comfort. It is built for survival. Human beings do not belong in space. That is the unspoken truth orbit teaches again and again. Every second aboard the station requires active resistance against an environment that would kill within moments if systems failed. Pressure must be maintained, oxygen carefully balanced, carbon dioxide scrubbed, temperature controlled, water recycled from sweat, breath, and waste. Nothing is wasted. Nothing is free. On Earth, life is supported passively by the planet itself. In orbit, life is a process, ongoing, fragile, and energy-intensive. This alone defines how far we can travel today. Because as long as humans require Earth-like conditions, we must carry Earth with us. And Earth is heavy. Every kilogram launched into orbit costs immense energy. Every additional system adds complexity. Every redundancy adds mass. Every safety measure increases the price. Space does not reward excess, it punishes it. So human spaceflight has become an exercise in minimization. Smaller crews, limited missions, carefully rationed supplies, everything optimized, nothing indulgent. Even so, the human body rebels. Within days of entering orbit, muscles begin to weaken. Without gravity, the body no longer needs to support itself. The muscles that evolved to fight gravity start to shut down. Bones follow. Calcium leaches away. Density decreases. Astronauts can lose up to 1 to 2% of bone mass per month despite rigorous exercise. On Earth, this would be catastrophic. In space, it is expected. The heart changes shape. Blood redistributes. Vision blurs as pressure builds in the skull. The immune system behaves unpredictably, sometimes weakening, sometimes overreacting. Space is not neutral. it is actively hostile to human biology. To counter this, astronauts spend hours each day exercising, running on treadmills with harnesses, lifting resistive devices designed to mimic weight. Exercise is not fitness in orbit, it is medicine, and still, damage accumulates. When astronauts return to Earth after long missions, they often cannot walk unassisted. Their balance is compromised, their strength diminished. Recovery takes weeks, sometimes months. This is the cost of going nowhere, of remaining close to Earth. Imagine extending this to deeper space. The limits become obvious. Radiation presents an even harsher constraint. Earth's magnetic field shields life from most cosmic and solar radiation. In orbit, this protection weakens. Beyond it, it disappears almost entirely. Radiation damages DNA. It increases cancer risk. It accelerates aging. It threatens cognitive function. Short missions tolerate this risk. Long missions magnify it. And deep space missions would compound it beyond anything yet experienced by humans. This is why, despite decades of orbiting Earth, humans have not ventured farther since the Apollo era. The Moon remains the farthest destination ever reached by living people. Not because we forgot how, but because we learned how dangerous it really is. Human spaceflight today is conservative by necessity. Every mission is weighed against risk, every extension debated, every failure scrutinized. Tragedies etched this caution into memory. Loss of crew, loss of vehicles, loss of confidence. Spaceflight is unforgiving, not because it is cruel, but because it is precise. Small mistakes cascade. Tiny flaws amplify. There is no margin for error when there is no air to breathe. This reality shapes how far we go. So instead of distance, we pursue duration. Instead of going farther, we stay longer. The longest continuous human presence in space spans months, sometimes close to a year. These missions are not about exploration. They are experiments in endurance. Can the body adapt? Can the mind endure isolation? Can systems operate without failure for extended periods? These are not abstract questions. They are prerequisites, because until humans can remain healthy in orbit indefinitely, deeper journeys remain theoretical. Psychology is as limiting as physiology. Humans are social creatures. Isolation warps perception. Confinement magnifies emotion. Minor annoyances grow teeth. Time stretches. Days blur. On the ISS, crews are carefully selected and trained to manage conflict, monotony, and stress. Communication with Earth is constant. Support is always available. Even then, tension exists. Now imagine removing Earth. Imagine messages delayed by minutes, then hours, then days. No real-time conversation, no immediate reassurance, no rapid rescue. This is not a challenge of courage. It is a challenge of identity. Human beings define themselves through connection. Distance erodes that connection. At some point, isolation stops being temporary and becomes existential. Human spaceflight today does not cross that threshold. And so, we remain close. Orbit is our comfort zone, uncomfortable as it is. It allows us to test systems without abandoning support, to experience weightlessness without surrendering rescue, to live in space without severing ties to Earth. This is the furthest sustainable human presence currently possible, but sustainability does not mean permanence. The ISS itself is finite. Its structure degrades. Its orbit decays. It requires constant maintenance. Eventually it will be decommissioned, guided to burn up in the atmosphere. When that happens, humanity will face a familiar choice: build another outpost or step back. Low Earth orbit is not destiny. It is training. Every hour spent there teaches us what breaks first: bodies, systems, minds, habits. It reveals that technology alone is not enough. Human beings must change, biologically, psychologically, culturally, if we are to travel farther. This is why the true limit of human space travel today is not measured in kilometers. It is measured in adaptation. How much change can we tolerate before we are no longer ourselves? Orbit demands small changes. Modified schedules, artificial gravity substitutes, medical monitoring. The Moon demands more. Radiation exposure, longer isolation, delayed communication. Mars demands transformation, years away from Earth. Permanent exposure to deep space, one-way risk. Beyond Mars demands something else entirely, something we are not yet prepared to become. So we linger, we perfect life support systems, we study bone loss, we monitor mental health, we simulate long missions in analog habitats on Earth, we debate ethics, funding, priorities. Human spaceflight today is not stagnant, it is cautious, and caution is not weakness, it is memory. We remember that every step outward costs lives if taken prematurely. We remember that space does not forgive impatience. We remember that survival is not guaranteed by ambition. So how far can humans travel through space right now? Physically, a few hundred kilometers above Earth, occasionally farther, briefly, with enormous effort, and always with a return planned. Emotionally, we still orbit home. Technologically, we stand at the edge of readiness, not yet over it. This is not failure. It is a phase. Humanity is not done learning how to leave Earth. We are still learning how not to die when we do. Mars has never stopped watching us. Long before rockets and radio waves, it burned in the night sky. Red, erratic, unsettling. Ancient civilizations gave it names soaked in fear and reverence. A wandering star, a god of war, a bad omen, a promise. It does not shine like Venus. It does not dominate like Jupiter. It lingers, faint, rust-colored, patient, and in that patience, it tempts us. Mars is close enough to imagine standing on, far enough to punish arrogance. It sits at the boundary between what humanity has done and what humanity claims it is ready to do. To ask how far we can travel through space right now is to collide, inevitably, with Mars, because Mars represents the first journey that cannot be undone easily. It is not a visit, it is a commitment. At its closest approach, Mars is tens of millions of kilometers away. At its farthest, hundreds of millions. The distance changes constantly as both planets orbit the Sun, locked in a slow cosmic dance that only occasionally brings them near each other. These windows, launch opportunities, open roughly every 26 months. Miss one, and you wait more than 2 years for the next. Space does not accommodate impatience. Travel to Mars takes months, not days, not weeks. Months spent coasting through deep space, exposed to radiation, isolation, and the psychological weight of knowing Earth is shrinking behind you, not beneath you. Once you leave Earth orbit, there is no turning around casually. This is the first truth Mars forces us to confront. Distance is not just space, it is time without refuge. On the way to Mars, there is nowhere to stop. No resupply, no emergency evacuation, no shelter beyond what you brought with you. Every system must work, for months. And then, after surviving the journey, Mars presents its second test: arrival. Mars does not welcome visitors. Its atmosphere is thin, too thin to slow a spacecraft safely without precise engineering, too thick to ignore. Landings are not graceful descents. They are violent negotiations with physics. Heat shields blaze, parachutes strain, retro rockets fire in desperate bursts. Every second is scripted. Every failure is fatal. This phase is known, without irony, as the 7 minutes of terror. Machines barely survive it. Humans would have no margin for error. But suppose we land. Suppose the engines cut off, the dust settles, and human beings step onto the surface of another planet for the first time. What then? Mars is not Earth's twin. That myth died long ago. It is cold, dry, irradiated. Its gravity is weaker, enough to function, not enough to protect long-term health. Its soil is toxic, its air unbreathable. It is not hostile in dramatic ways. It is hostile in quiet ones. There are no storms that tear habitats apart most of the time. No predators, no sudden cataclysms. Instead, there is a constant erosion of safety. Radiation rains down daily, Dust infiltrates everything. Machinery degrades. Bodies adapt in unpredictable ways. Mars does not kill you instantly. It dares you to stay. And staying is the real challenge. Short missions are conceivable. Land, explore, collect samples, leave. But Mars does not justify that risk for a brief visit. The cost is too high, the danger too great. If humans go to Mars, they will go to remain, at least for years. And that changes everything. Because a Mars mission is not a voyage. It is an experiment in civilization. Crews would need to bring or generate air, water, food, power, medicine, spare parts, and psychological resilience, all without Earth's immediate support. Communication delays stretch from minutes to nearly half an hour round trip. Conversations become letters, emergencies become isolation. Decisions must be made locally. Mistakes cannot be undone remotely. Mars demands autonomy. This is where the dream begins to fracture. Not because Mars is unreachable, but because Mars requires humans to accept a new relationship with Earth, one defined by separation. On Mars, Earth is no longer home. It is history. Astronauts in orbit look down and see continents drift beneath them. Astronauts on Mars will look up and see Earth as a bright star, sometimes not visible at all. This psychological distance is unprecedented. No human has ever lived knowing that return is not guaranteed, not because of courage, but because of orbital mechanics. A Mars crew cannot leave whenever they choose. They must wait for planetary alignment, sometimes for more than a year. They must survive until the window opens. Mars is not forgiving of impatience or fear. It forces endurance. Biology strains under this demand. Radiation exposure during a Mars mission could exceed safe lifetime limits. Muscle and bone loss accumulate over years. The immune system adapts unpredictably. Mental health risks compound under isolation and monotony. And unlike orbit, Mars gravity is not enough to fully preserve health, but enough to complicate recovery. We do not yet know what long-term life in partial gravity does to the human body. We do know it is a gamble. Technology strains too. Life support systems must be closed-loop. Every molecule recycled. Every failure diagnosed without replacement. Every repair improvised. On Earth, redundancy is solved by supply chains. On Mars, redundancy is solved by foresight. This is why, despite constant headlines and bold timelines, no human mission to Mars has yet occurred. Not because we lack rockets, but because we lack certainty. We are still learning how to survive away from Earth for long durations. Orbit teaches us months. The Moon may teach us years. Mars demands decades of reliability, compressed into a single mission. It demands perfection, or forgiveness for imperfection. And space offers neither. Even politically, Mars resists haste. A Mars mission would span multiple governments, budgets, generations of leadership. Commitment must outlast elections. Vision must survive shifts in priority. Mars does not care about deadlines. It waits. Some propose that Mars is necessary, a backup world, a second home, an insurance policy against extinction. Others argue that it is a distraction, that Earth's problems cannot be escaped by exporting humanity elsewhere. Both are partly right. Mars is not salvation, it is rehearsal, a test of whether humanity can extend itself beyond the cradle without breaking. This is why robotic missions have gone first. Orbiters mapping terrain, rovers drilling soil, probes sniffing air for ancient traces of life. Machines scout, humans hesitate. Because Mars is not just a destination, it is a mirror. It reflects our readiness, not technologically, but culturally. Are we willing to send people so far away that help cannot reach them in time? Are we willing to accept deaths without rescue? Are we willing to build societies where isolation is permanent? These are not engineering questions. They are ethical ones. At present, humanity's answer is cautious silence. We talk, we plan, we simulate, but we do not launch. This reveals the true boundary of human space travel right now. It is not low Earth orbit. It is not the moon, it is commitment without retreat. Mars sits just beyond that line, close enough to tempt us, far enough to expose hesitation. We will go to Mars someday. That much is almost certain. The question is not if, it is who we will be when we do, because the version of humanity that can survive Mars is not the version that exists today. It will require new tolerance for risk, new definitions of success, new acceptance of loss. It will require us to loosen our grip on Earth, emotionally, politically, culturally, and we are not there yet. So Mars remains a frontier in waiting, a red threshold we orbit with our imaginations but have not yet crossed with our bodies. Beyond Mars, the solar system changes character. The warmth fades. The light weakens. The sun, once a blazing presence, becomes a brilliant star among many. This is where the inner worlds end and the outer worlds begin, where distance stops feeling merely large and starts feeling punitive, where time stretches, communication thins, and the human body becomes an ever greater liability. If Mars is the threshold, humanity hesitates before crossing, then the outer solar system is the abyss we barely dare to name. Jupiter, Saturn, Uranus, Neptune. They are not destinations in the human sense. They are regimes, ruled by forces that do not tolerate life as we know it. Crushing gravity, radiation belts that could sterilize unprotected flesh in hours. Temperatures that freeze atmospheres solid. And yet these giants dominate the solar system. They shape its architecture. They guard its outer reaches like ancient sentinels. To ask how far humans can travel right now is to recognize an uncomfortable truth. Mars is likely the farthest planet humans will reach for a very long time. Everything beyond it belongs, for now, to machines. Distance alone makes this clear. Mars sits, on average, about 225 million kilometers from Earth. The outer planets begin hundreds of millions of kilometers farther still. Jupiter alone can be more than 900 million kilometers away. Saturn doubles that. Neptune pushes beyond 4 billion. Travel times expand accordingly. A journey to Jupiter would take years, not months, even with optimal trajectories. A journey to Saturn would take longer still. And unlike Mars, these are not journeys towards surfaces that can be lived on. They are journeys into environments that kill. Jupiter, the largest planet in the solar system, is a world of violence. Its gravity well is immense. Its storms dwarf Earth. Its radiation belts are lethal, the most intense in the solar system. A human approaching Jupiter without extraordinary shielding would receive a fatal dose of radiation long before arrival. There is nowhere to land, no solid ground, no refuge. Saturn, serene from afar, is no kinder. Its rings are beautiful, but beauty in space is often a warning sign. Ice particles orbit at lethal velocities. Its atmosphere crushes and freezes. Its gravity traps. The outer planets are not worlds to visit, they are forces to endure. Some look to their moons instead, icy spheres hiding subsurface oceans. Europa, Enceladus, Titan. These moons are scientifically fascinating. They may harbor life. They are among the most compelling destinations for exploration in the solar system. But compelling does not mean accessible. Reaching these moons requires passing through the gravity wells and radiation fields of their parent planets. It requires years of transit. It requires systems that can operate without sunlight strong enough to power solar panels. And then, upon arrival, it requires landing on surfaces colder than Antarctica, under skies darker than any night on Earth. For robots, this is difficult. For humans, it is catastrophic. The outer solar system exposes a brutal scaling law. As distance increases, survivability decreases faster than technology improves. Life support systems become heavier, radiation shielding thickens, power requirements grow, redundancy multiplies. Every additional year of travel compounds risk. This is why human missions do not even exist on paper for these worlds. Not seriously, not with timelines. Because the outer solar system demands not just endurance, but transformation. A human mission to Jupiter's moons would likely require artificial gravity habitats, nuclear power, advanced radiation shielding, autonomous medical systems, and psychological architectures we have never tested. It would require humans to live in space not for months or years, but for decades. And even then, the destination would offer no sanctuary. This reveals a fundamental truth. The solar system is not scaled for human travel. It is scaled for gravity, radiation, and time. We are visitors here, tolerated briefly, punished swiftly. Machines thrive where humans fail. Robotic probes do not mind darkness. They do not age. They do not fear radiation. At least not in the way cells do. They can coast for decades, sleep through long journeys, wake only when needed. This is why every world beyond Mars we know in detail was revealed by machines. Flybys of Jupiter exposed its storms and moons. Probes unveiled Saturn's rings. Orbiters mapped Uranus and Neptune in fleeting passes. Humans did not follow. We watched from afar, and as we watched, another realization settled in. Distance is not the only barrier, velocity is. The farther from the sun you travel, the weaker gravity becomes, and paradoxically, the harder it is to maneuver. Slowing down costs fuel. Entering orbit costs fuel. Landing costs fuel. Every maneuver compounds mass. Human spacecraft are already burdened by life support. Adding fuel for deep space braking pushes missions beyond feasibility. Robots can accept flybys. Humans need destinations. This mismatch defines the outer solar system. But suppose we solved these problems. Suppose we had propulsion powerful enough to shorten travel times. Suppose we had radiation shielding robust enough to protect crews. Suppose we had habitats capable of sustaining life indefinitely. Even then, the outer solar system confronts us with a quieter challenge. Isolation. A human mission to the outer planets would leave Earth behind not for years, but for a significant fraction of a lifetime. Communication delays would stretch to hours. Emergencies would be handled alone. Return would be uncertain. Such missions are not expeditions. They are exiles. Human psychology evolved in tribes, not in steel cylinders drifting through eternal night. The mind does not cope well with infinite horizon and delayed reassurance. We are still learning how to manage isolation measured in months. The outer solar system demands mastery of isolation measured in decades. And so, for now, humanity draws a line. Mars is the edge. Beyond it, ambition fades into caution. This does not mean the outer solar system is unreachable forever. It means it belongs to a different era, one where humans may not resemble us as we are now. Perhaps they will be genetically adapted, perhaps cybernetic, perhaps culturally transformed into beings comfortable with silence and time. But those humans do not exist yet. And until they do, the outer solar system remains a place we study, not inhabit. Beyond the orbit of Neptune, the solar system dissolves into a vast halo of debris, the Kuiper belt, then the hypothetical Oort cloud. These regions are so distant that even our probes will take centuries to traverse them fully. Here, the sun's authority weakens until it finally yields. Interstellar space begins quietly. No boundary marker, no gate. Just a gradual thinning of influence. This is the final frontier of the solar system, and the beginning of something far larger. For machines, crossing it is inevitable. For humans, it is inconceivable. For now. The outer solar system teaches us humility. It reminds us that the universe is not obligated to accommodate us, that our presence here is conditional. That survival is local, not universal. And yet, it also teaches patience. Every probe launched into these regions is a message to the future. Every dataset expands our understanding. Every failure informs the next attempt. We are not stalled. We are accumulating wisdom. Human space travel does not advance by bravado. It advances by restraint, and in that restraint lies the possibility of endurance. If distance defines the limits of space travel, propulsion defines the possibility. No matter how much we dream, how much we desire, or how much we build, we are bound by the mechanics of motion. Space does not forgive imagination that ignores physics. It does not yield to willpower. Every journey begins with force, and every journey is constrained by the energy required to sustain it. To understand how far humans, or even machines, can travel through space today, we must confront the engines, fuels, and laws that govern motion in the cosmos. 1. Newton's universe, the rule of motion. The first law of motion is deceptively simple. An object in motion stays in motion unless acted upon by an external force. In space, where friction is negligible, this principle is both liberating and limiting. Once a spacecraft is moving, it can coast indefinitely. No engine required. But starting, stopping, and changing direction are another story entirely. Every maneuver requires delta V, a measure of the change in velocity, which directly correlates with the energy and fuel needed. This is where human limitations meet cosmic realities. In orbit, in transit to Mars, even in interstellar space, the challenge is not coasting, it is acceleration, and acceleration is expensive. Even small velocity changes consume massive amounts of fuel, especially when moving masses as large as crewed spacecraft. Every kilogram added to a ship, supplies, water, air, people, multiplies the energy required. This is known as the tyranny of the rocket equation, formulated by Konstantin Tsiolkovsky over a century ago. The equation is brutally simple and brutally unforgiving. To increase the final speed of a spacecraft, you need exponentially more fuel. Each increment of velocity costs more than the last. This is why traditional rockets rely on multi-stage designs, shedding weight gradually to maintain efficiency. Even then, energy demands grow quickly. 2. Chemical rockets, the current standard. Today, human space travel depends on chemical propulsion. Rockets burn fuel to produce hot gas, expelled at high velocity, generating thrust in accordance with Newton's third law. For every action, there is an equal and opposite reaction. Chemical rockets are powerful, capable of escaping Earth's gravity, reaching the Moon, and sending probes to the outer planets. Saturn V, the most powerful rocket ever flown, produced 7.5 million pounds of thrust at launch. It carried humans beyond the Earth-Moon system, an achievement unmatched in the decades since. Yet chemical propulsion has limits. The speed achievable is constrained by fuel mass and combustion energy. To reach even a fraction of the distance to Mars efficiently, chemical rockets suffice. Beyond Mars, energy requirements increase beyond practical limits. To approach Jupiter or Saturn with crewed missions, chemical rockets become almost useless without staging, nuclear augmentation, or new technologies. This is why nearly all current deep space travel beyond humans is robotic. Machines are lighter, expendable, and can afford extremely long acceleration periods using low-thrust engines. 3. Ion and electric propulsion. Efficiency over power. Enter the era of ion drives and electric propulsion. Unlike chemical rockets, which produce large amounts of thrust for short durations, ion drives produce small amounts of thrust continuously over years, gradually accelerating spacecraft to speeds that would be impossible with chemical fuel alone. Ion engines work by ionizing a propellant, typically xenon, and expelling ions using electric fields. The exhaust velocity is much higher than chemical rockets, meaning more efficient use of fuel. The trade-off, the thrust is minimal. Take Dawn, the NASA mission to Vesta and Ceres. It accelerated so slowly that astronauts would have felt almost nothing if aboard, yet over years, it achieved incredible speeds. Ion propulsion exemplifies a key truth of space travel. Time substitutes for brute force. You cannot always go fast immediately, but patience allows speed to accumulate. For human travel, however, time is not as flexible as it is for machines. Humans age, supplies dwindle, life support systems degrade. Ion drives are perfect for unmanned probes, less so for crews unless combined with cryogenic hibernation or life-extending technology. 4. Nuclear and fusion propulsion, dreams of the future. If chemical and ion engines illustrate the present, nuclear and fusion drives hint at the possible future. Nuclear thermal rockets, fission-based engines, promise twice the efficiency of chemical rockets. They heat propellant using nuclear reactions, achieving higher exhaust velocities and reducing fuel mass requirements. Fusion propulsion, still theoretical, would be a revolution. By fusing light elements like hydrogen isotopes, a spacecraft could generate orders of magnitude more energy than chemical reactions. Theoretical designs suggest continuous acceleration capable of propelling humans to Mars in weeks, or even reaching outer planets within human lifetimes. These technologies are tantalizing because they confront the fundamental barrier of energy density. Space is vast, and pushing a massive ship over millions of kilometers requires tremendous energy. Only nuclear or fusion systems offer sufficient power without needing impossible quantities of fuel, but challenges remain. Radiation, reactor control, shielding, and material engineering are unresolved. Fusion has eluded practical energy production on Earth, let alone on a spacecraft. And until these problems are solved, human travel remains constrained by chemical and conventional propulsion. 5. Gravity assists, borrowing cosmic energy. Even without revolutionary engines, humanity has learned to borrow energy from the planets themselves. Gravity assists, or slingshots, use a planet's motion to accelerate a spacecraft, stealing a fraction of the planet's orbital energy. Voyager 1 and 2, New Horizons, and countless other probes relied on this technique to reach the outer solar system. It is elegant, efficient, and cost-free in terms of fuel. For humans, gravity assists are still used. For example, missions to Mars may use Earth or Venus flybys to reduce fuel consumption. Yet this technique is constrained by alignment windows and trajectory planning. It is not a substitute for onboard propulsion, it merely augments it. It also illustrates a deeper principle. Space travel is a negotiation with the universe. You cannot overpower physics, you must exploit it. 6. Limits imposed by physics. Even with perfect engines, physics sets unbreachable limits. The speed of light, roughly 300,000 km/s, is the ultimate speed limit. No amount of propulsion can exceed it. For human travel beyond the solar system, this limit is crushing. The nearest star is 4.2 light-years away. At 0.1% of light speed, a spacecraft would take over 4,000 years to arrive. Even at 10% of light speed, we are talking decades-long journeys, still longer than most human lifespans. Then there is the mass energy problem. As velocity increases, relativistic effects cause the effective mass of a spacecraft to rise, requiring ever more energy for further acceleration. Approaching significant fractions of light speed requires energies that are simply unattainable with current or near-future technology. And space itself is not empty. Tiny particles, micrometeoroids, and cosmic rays become lethal hazards at high speeds. At 10% of light speed, even a single dust particle impact could destroy a spacecraft. Every proposed propulsion technology must contend with these immutable laws. Energy, mass, and time are intertwined. You cannot cheat one without paying a cost in another. 7. Practical implications for human travel today. All of this returns us to the central question: how far can humans travel right now? The answer is shaped entirely by propulsion limits. Low Earth orbit, easily reachable using chemical rockets. Crew can survive and return safely. Current practice: Moon, within reach using chemical rockets with multi-stage designs and careful planning. Temporary stays possible. Mars, reachable theoretically using chemical rockets, ion augmentation, or nuclear thermal propulsion. Current human missions are limited by life support, radiation, and duration, not yet feasible on a routine basis. Outer planets, not human reachable with current propulsion, requires decades-long journeys, enormous shielding, and life support systems beyond current capability. Only robotic probes can safely traverse these distances. Interstellar space, far beyond present human capability. Machines may arrive over centuries. Humans would require breakthroughs in propulsion, energy, and biology. Despite current constraints, propulsion research offers hope. Nuclear, fusion, antimatter concepts, and beamed energy systems could eventually allow human crews to travel farther and faster. Advanced life support and artificial habitats may extend endurance. Cryogenic hibernation may circumvent aging constraints. But even with breakthroughs, speed will remain a central barrier. Humanity cannot escape time. Every increase in distance multiplies the challenge of survival, supplies, and communication. In other words, the farther we go, the more we must redesign ourselves and our machines. Propulsion is not merely a technical problem, it is a philosophical one. It forces us to consider, how much risk can humans tolerate? How much delay is acceptable? How much transformation is acceptable to survive? Physics does not negotiate. It does not reward ambition. It imposes the rules, and we must adapt. Every civilization has looked up at the stars and wondered what lies beyond. Every dream of leaving Earth collides with the same immutable question: how far can we go? Within our solar system, the answer is bounded by physics, engineering, and biology. Beyond it, into interstellar space, the constraints become almost incomprehensible. The distances are not vast in the sense of kilometers or miles, but in human terms, in lifetimes, generations, and cosmic patience. Interstellar space begins where the sun's influence ends. The heliopause, crossed first by Voyager 1 and 2, marks our departure from the protective bubble of our star. Beyond it lies the vast expanse of empty dark matter and radiation, stretching toward the nearest stars. For humans, interstellar space is more than a vacuum. It is a challenge of time, endurance, and imagination. 1. Distances that defy comprehension. The closest star system to Earth, Alpha Centauri, is 4.37 light-years away. To put that in perspective, light, the fastest entity in the universe, takes over 4 years to bridge this gap. Compare that to our current human limits. Low Earth orbit, 400 kilometers. The Moon, 384,000 kilometers. Mars, 225 million kilometers. The distances grow by orders of magnitude, and suddenly the solar system seems like a small pond compared to the vast cosmic ocean beyond. Current propulsion technology cannot make this journey feasible within a human lifetime. A spacecraft traveling at the speed of the fastest human-made object, Voyager 1, would take over 70,000 years to reach Alpha Centauri. Even if we imagined a craft traveling at 10% of light speed, an ambitious but far future goal, the trip would take decades. The scale is sobering. Distances that are trivial for light become eternal for flesh. Interstellar ambition confronts us with the first stark limit. Human lifespans are short relative to cosmic distances. 2. Propulsion challenges. Chemical rockets? Insufficient. Ion drives? Too slow for human crews over interstellar distances. Nuclear or fusion propulsion? Theoretical. Antimatter engines? Conceptual. The energy required to accelerate a spacecraft to even a significant fraction of the speed of light is staggering. Mass grows exponentially with speed due to relativistic effects, and shielding against interstellar radiation becomes an existential concern. Every particle in the void, every stray cosmic ray, can cause catastrophic damage at high velocities. Even assuming perfect propulsion, the human body faces relentless stress. Extended exposure to cosmic radiation, microgravity or artificial gravity conditions, and isolation for decades or centuries presents unsolved physiological and psychological problems. We could, in theory, send generation ships, massive vessels where multiple human generations live and die during the voyage. But this transforms space travel into a new form of society, one where life is entirely ship-bound, and survival depends on the stability of a self-contained civilization. In other words, interstellar travel forces a radical redefinition of what it means to be human, biologically, socially, and psychologically. 3. Life support across light years. Sustaining life for decades, possibly centuries, requires closed-loop life support systems far beyond what has ever been attempted. Water, air, and food must be recycled with near-perfect efficiency. Waste cannot be discarded, it must be converted. Energy sources must be long-lasting and reliable, possibly nuclear or antimatter-based. The human mind must be preserved too. Isolation, monotony, and lack of contact with Earth pose psychological hazards unprecedented in human history. Society aboard such a ship would need to manage conflict, governance, and cultural continuity, ensuring that knowledge, skills, and purpose persist through generations. Even small system failures could escalate into catastrophe. A minor breach in oxygen recycling or water purification could doom the ship. Interstellar travel is unforgiving. There is no margin for error. 4. Communication, delays, and isolation. In interstellar space, communication with Earth becomes impractical. Even at the speed of light, messages take years to travel. For a mission to Alpha Centauri, a single round-trip message could take over 8 years. Real-time assistance, resupply, or consultation is impossible. Humanity must accept profound isolation. The crew must be autonomous, able to make all decisions without hope of guidance. This is a radical departure from every precedent of human exploration. On Earth or in orbit, we rely on immediate feedback, rescue, and support. In interstellar space, those luxuries vanish. 5. Cosmic hazards. The vacuum of interstellar space is not empty. High-energy particles, micrometeoroids, and cosmic radiation pose constant threats. At speeds approaching even a fraction of light, collisions with dust or gas could puncture hulls, destroy electronics, and imperil life. There are no familiar landmarks. Navigation relies on distant stars, pulsars, and meticulous calculations. Time itself becomes relative. Relativistic effects mean that the passage of time for travelers differs from that experienced on Earth, adding a subtle layer of disconnection from home. 6. Machines versus humans. In contrast, robotic explorers can traverse these distances more feasibly. They can endure decades or centuries of travel, operate under minimal energy, and handle delayed commands. Voyager 1 and 2, launched in the 1970s, are humanity's first interstellar ambassadors, carrying messages, instruments, and symbols of our civilization. Humans cannot yet replicate that endurance. Our limitations, physiological, psychological, and logistical, define the boundary of present human travel. Interstellar ambition exists primarily in imagination, theory, and machine-mediated exploration. 7. The question of motivation. Why attempt interstellar travel at all? The motivations are philosophical, not technical: curiosity, survival, expansion of knowledge, or the desire to become a multi-star species. Yet motivation does not alter reality. Even with perfect intent, the universe imposes limits. Humanity's reach is defined by our bodies, technology, and patience. Interstellar travel exposes the gap between aspiration and capability. It is a confrontation with the immensity of time and space, where ambition meets the immutable laws of physics. 8. Future possibilities. There are speculative solutions: cryogenic sleep, genetic enhancement, artificial intelligence companionship, or post-human consciousness transfer might extend endurance. Propulsion breakthroughs, antimatter, warp drives, or harnessing exotic physics could shrink effective travel time. Yet all remain hypothetical. Today, interstellar travel is a thought experiment, a horizon humanity can see but cannot yet approach. It is a reminder that space is vast, indifferent, and infinitely patient. The lesson is clear. Our limits are not only technical, but human. We can reach only as far as our bodies, minds, and societies permit. Beyond that, we rely on probes, imagination, and the slow accumulation of knowledge. 9. A cosmic perspective. The distances involved recalibrate perspective. Earth, the Moon, Mars, and even the outer planets become minor outposts in a vast cosmic sea. The Milky Way alone spans 100,000 light-years. Stars are scattered sparsely. The nearest beyond Alpha Centauri are decades away at even near light speed. Our ambition outpaces our capability. The universe is patient. Our curiosity is not constrained by time. Machines carry our dreams, gradually expanding our reach. Humans remain tethered to the solar system, orbiting its boundaries, testing endurance, gathering knowledge, and preparing for what may come. 10. Interstellar travel as a mirror. Ultimately, interstellar ambition is as much about humanity as it is about space. It reflects our desire to leave a mark, to endure, to explore. It exposes our fragility and resilience. It challenges us to confront mortality, distance, and the laws of physics simultaneously. The further we aim, the more we understand ourselves. The void of interstellar space is not merely a destination. It is a mirror of our limitations, ingenuity, and imagination. Even as robotic probes drift into the void, sending back whispers of stars, we remain at the threshold. Interstellar travel is not yet our reality, but it defines the horizon, a frontier that shapes our present understanding of how far we can go. Every civilization, from the first humans who gazed up at the night sky to the modern physicists peering through their telescopes, has asked the same question: how far can we go? It is a question that humbles, terrifies, and inspires. We have traced the journey from the safety of Earth's surface to low orbit, from the Moon to Mars, from the outer planets to interstellar space. Along the way, we have discovered that distance is not merely a measurement. It is a framework defined by physics, biology, psychology, and imagination. 1. The scope of human achievement today. At this moment, the furthest humans have traveled from Earth is the Moon, a mere 384,000 kilometers away. That journey, brief and perilous, represents the peak of human physical space travel. Low Earth orbit, home to the International Space Station and continuous human presence, demonstrates our ability to survive in microgravity, manage life support systems, and live in confined, isolated environments for months or even years. Yet beyond this, distance becomes an increasingly unforgiving boundary. Mars looms as the first challenge that cannot be addressed by human endurance alone. To reach it safely, humans must contend with months of travel, radiation exposure, and profound isolation. The Moon was a short leap. Mars is a voyage of commitment. Every milestone, orbit, moon landing, long-duration ISS missions, serves as a lesson. We learn not just how to survive, but how fragile life is in the void. Systems fail, bones weaken, minds strain, and yet humans adapt, slowly and deliberately, to extend the frontier further. 2. Machines as our pioneers. Where humans cannot yet reach, machines have gone. Robotic explorers are the vanguard of our species, carrying instruments, cameras, and messages into places no human could survive. Voyager 1 and 2, New Horizons, Pioneer 10 and 11. These spacecraft traverse the solar system and beyond, untouched by the limitations of flesh. They coast for decades, powered by radioisotope thermoelectric generators. They endure radiation, cold, and the silence of interstellar space. The distinction is stark. Machines can explore far beyond human reach. They can travel thousands, millions, and eventually billions of kilometers, while humans remain confined to orbital and near-planetary habitats. They operate under constraints of energy and time, but not biology. They extend our reach, not our bodies. Machines are also teachers. They reveal the nature of the solar system, the hazards of deep space, and the mechanics of trajectories that may one day carry humans farther. Every signal from Voyager or New Horizons is a whisper from the future, reminding us both of the vastness beyond our grasp and the ingenuity we possess to probe it. 3. The the solar system as our laboratory. The solar system is our first classroom in deep space. Each planet, moon, and asteroid teaches lessons about survival, engineering, and the physics of motion. Low Earth orbit teaches the fragility of the human body. The moon demonstrates the difficulty of landing and returning from a celestial body. Mars exemplifies endurance over months and years. The outer planets, by contrast, illustrate the tyranny of distance. Jupiter and Saturn are unreachable for humans with present technology. Their moons, while fascinating, are environments of extreme cold, radiation, and logistical impossibility. Uranus and Neptune lie even further, where travel times would span human lifetimes. Every lesson reinforces the central theme. The distance humans can travel is defined not just by ambition, but by survival. The farther we attempt to go, the more our biology, psychology, and technology are tested. Robotic exploration helps us prepare. Each probe acts as a scout, mapping hazards, testing trajectories, and demonstrating the realities of radiation, temperature, and isolation. These lessons form the foundation for eventual human travel beyond Mars. 4. The physics of travel. No discussion of distance is complete without considering the laws of physics. Propulsion, energy, and velocity define the upper limits of human reach. Chemical rockets suffice for the Moon, Mars, and possibly the inner solar system. Ion drives extend travel times for probes to the outer planets. Nuclear and fusion technologies promise the possibility of deep space human missions in the future. Yet fundamental constraints remain. The rocket equation dictates that every increase in velocity requires exponentially more fuel. Even theoretical propulsion methods, antimatter, fusion, or beamed energy drives, encounter limits imposed by mass, energy, and radiation hazards. The speed of light remains an unbreachable barrier, defining the scale of interstellar distances relative to human lifespans. Thus, physics is both guide and governor. It enables progress while imposing boundaries that cannot be ignored. 5. Interstellar horizons. Interstellar travel remains beyond current human capability. The nearest star system, Alpha Centauri, is 4.37 light-years away. With current technology, travel times would span millennia. Even optimistic designs, such as generation ships or cryogenic sleep, confront unresolved challenges in life support, psychology, and energy. For now, the universe beyond the solar system is accessible only to machines. Robotic probes may take centuries to reach other stars. They will carry data, artifacts, and perhaps human messages, but not flesh and blood. Humans, constrained by biology and lifespan, are limited to the solar system, awaiting technological breakthroughs that may one day extend our reach. 6. The human element. Distance is not measured solely in kilometers. It is measured in resilience, endurance, and adaptation. Low Earth orbit teaches that humans can survive in microgravity for months. Mars teaches that survival over years requires careful engineering, psychological preparation, and societal adaptation. The outer planets teach that humans cannot yet endure decades of transit without revolutionary technology. The psychological dimension is profound. Humans are social beings, adapted to life on a planet with gravity, atmosphere, and predictable cycles. Isolation, communication delays, and permanent separation from Earth pose challenges as difficult as radiation or vacuum. The farther we travel, the more we must adapt ourselves culturally, socially, and biologically. 7. Technology as extension. Machines extend human reach. Advanced life support, propulsion, and habitat design extend human endurance. Automation and artificial intelligence help manage the complexity of interplanetary and interstellar journeys. Yet technology is only an extension, not a substitute. It allows humans to go farther than biology alone would permit, but it does not erase the fundamental limitations imposed by distance and physics. In essence, Our current frontier is defined by the synergy of human biology and engineered systems. Each achievement, from orbital missions to Mars analog habitats, teaches us how to push this boundary safely. 8. The future of human travel. Looking forward, there are clear milestones. Mars. The first human mission will test life support, radiation protection, and long-duration spaceflight. It will require years of preparation and will redefine human endurance. Outer solar system. Crewed missions are improbable in the near term. Probes will continue to explore, mapping hazards and informing future strategies. Interstellar travel, a distant aspiration. Machines will go first. Human travel will require breakthroughs in propulsion, life support, and perhaps even human biology. Even these milestones will depend on international cooperation, technological ingenuity, and philosophical willingness to accept risk. Space is not forgiving, and every step outward increases the stakes. 9. The role of curiosity. Ultimately, distance is both limit and motivation. Humanity does not explore merely because it can, but because it must. Curiosity drives us to build, to innovate, to endure. Machines carry our curiosity farther than we can go ourselves. Each signal, image, and measurement bridges the gap between ambition and capability. Curiosity is what ensures that humans will eventually overcome present limitations. It is what inspires engineers to design better propulsion, doctors to understand radiation effects, and psychologists to prepare crews for isolation. It is what allows the imagination to stretch across light years, even when the body cannot follow. 10. How far can we travel right now? Returning to the central question. Physically, humans are limited to low Earth orbit and near-term moon missions. Mars is within sight, but not yet safely reachable. Technologically, machines can travel beyond the solar system. Robotic probes have reached interstellar space. Humans rely on life support, propulsion, and engineering to extend reach incrementally. Conceptually, interstellar travel exists in theory, constrained by physics, time, and human biology. It challenges us to rethink society, life, and endurance. Distance is a relative measure. Machines extend the reach of human influence. Humans extend the reach of human experience. Together, they define the practical and philosophical boundaries of travel through space. 11. A cosmic perspective. Viewed from afar, Earth is a pale blue dot. Voyager 1's iconic image reminds us of our fragility, our tiny place in the cosmos, and the ambition that drives us to leave it. The distances we have covered physically are dwarfed by the scale of the solar system and galaxy. Yet our probes, orbiters, and astronauts demonstrate that exploration is possible, limited only by patience, ingenuity, and courage. The solar system is our laboratory. The stars are long-term aspiration. We inhabit one, prepare for the other. We send machines to distant worlds and dream of sending ourselves. The universe is vast, indifferent, and patient. Our presence is fleeting, but our curiosity endures. 12. The final reflection. So, how far can we travel through space right now? We can orbit the Earth, sustaining life for months at a time. We can touch the moon briefly, leaving footprints and returning safely. We can send robots to Mars, the outer planets, and beyond, into interstellar space. We cannot yet reach Mars as humans with current safety and reliability standards. Interstellar travel for humans remains beyond reach, limited by lifespan, propulsion, and physics. Yet the very act of asking the question propels us forward. Every probe, rocket, and mission represents an attempt to expand that boundary. Every image from the Moon, Mars, or Voyager whispers a reminder. The universe is vast, but so is human ambition. In the end, the measure of our travel is not simply in kilometers. It is in curiosity, resilience, ingenuity, and courage. It is in the knowledge that every meter we move outward carries us farther in understanding, not just of space, but of ourselves. And that is where the true journey begins. We have not yet reached the stars, but with each mission, each technological advance, and each human heartbeat in orbit or on another world, we move farther than ever before and dream farther still. Every step we have taken into space has been a negotiation with the unknown. From the first rockets piercing Earth's atmosphere to robotic emissaries venturing into interstellar darkness, humanity has tested its limits repeatedly. But beyond the mechanics, beyond propulsion and distance, lies the most profound frontier, the future of humanity itself. To ask how far we can travel is not only to ask how far a rocket can go, it is to ask, how far can we go? How far can human culture, biology, and civilization stretch before the universe imposes limits too great for our species to endure? 1. Humanity at the threshold. Low Earth orbit and the Moon are our laboratories. Mars looms as the first true test of endurance, isolation, and autonomy. The outer planets remain unreachable for humans with current technology. Interstellar space belongs to machines. Yet the human imagination refuses to stop. We dream not only of going farther, but of evolving to survive farther. This is not mere fantasy. Our biology, society, and technology are all subject to evolution. Slow, deliberate, and now accelerating through artificial means. Space, more than any other environment, forces adaptation. Microgravity changes muscles, bones, and hearts. Radiation alters DNA. Isolation challenges cognition and culture. The farther we go, the more we must transform ourselves. Every frontier beyond Earth imposes selection pressures. These pressures are physical, yes, but also cultural and psychological. Survival depends on cooperation, knowledge, patience, and innovation. 2. Cultural evolution in space. Consider Mars. Even with the most advanced life support systems, humans cannot survive as they do on Earth. Societies on Mars will be small, interconnected, and highly dependent on engineered systems. They will create cultures dictated by necessity, strict rules, shared responsibilities, and collective memory to preserve critical knowledge. Cultural evolution will accelerate in these conditions. Norms, rituals, and hierarchies may emerge rapidly to maintain stability. Mars-born generations may think differently from Earth-born humans, not just in practical ways, but philosophically, socially, and emotionally. Beyond Mars, in orbiting habitats or deep space vessels, this divergence will be even more pronounced. Humans may evolve to tolerate isolation, long-duration confinement, or altered gravity. They may prioritize collective survival over individual freedom. Language, art, and ritual may change to fit new environmental realities. The culture of humans in deep space will become a laboratory for evolution itself, an acceleration of social, cognitive, and ethical adaptation, driven not by survival in forests or cities, but in steel, vacuum, and radiation. 3. Biological adaptation. Physical evolution in space is more subtle but no less consequential. The human body is adapted to a 1G environment. Long-term exposure to microgravity or partial gravity forces physiological change. Bones demineralize, muscles weaken. The cardiovascular system redistributes fluid. Even reproduction, growth, and immunity are affected in ways we are only beginning to study. Artificial habitats and medical technology can compensate, but only partially. Over generations, humans may require genetic adaptation to thrive in altered gravity or radiation-rich environments. Whether through natural selection, genetic engineering, or symbiosis with protective technology, space may force a divergence in human biology. In other words, humanity's future in the stars may not be the humanity we know today. It may be taller, shorter, stronger, or more resilient. It may see differently, metabolize differently, or think differently. The universe does not demand conformity. It rewards adaptability. 4. Psychological evolution. Equally critical is the mind. Isolation, confinement, and distance from Earth impose unique psychological pressures. Astronauts experience disorientation, altered sleep cycles, and emotional strain in orbit. Imagine these pressures multiplied over years or decades, as in a mission to Mars or a generation ship to Alpha Centauri. Humans may evolve cognitive and emotional strategies to cope. Empathy may shift from Earth-centric to crew-centric. Problem-solving may rely more on pre-planned protocols than improvisation. Identity may become tied less to geography and more to habitat. We may even see new modes of consciousness emerge. Digital augmentation, neural interfaces, or hybrid AI-human cognition could enable minds to thrive in environments that currently threaten human sanity. Space travel is as much a challenge for consciousness as it is for muscles or bones. 5. Ethical considerations. As we contemplate colonizing other worlds, ethical questions multiply. Who decides who travels? Who governs distant habitats? What are our obligations to Mars, moons, or exoplanets that may harbor life? Colonization is not merely logistical, it is moral. Every choice, from resource extraction to genetic modification, carries consequences for future generations. The farther humans go, the less direct oversight there is from Earth. Governance must become autonomous, fair, and adaptive. Ethics in space may evolve faster than ethics on Earth. Rules that work for crowded cities may fail in isolated habitats. Decisions that seem trivial on Earth, how to ration water, who repairs life support, how to manage conflict, become existential in space. 6. The role of technology as partner. Technology is no longer just a tool, it becomes a partner in survival. Life support, propulsion, AI companions, medical automation, and even cybernetic enhancements extend human capability. These technologies allow us to survive where biology alone would fail. Yet technology is not neutral. It shapes behavior, culture, and identity. AI may become the arbiter of decisions in distant habitats. Automation may redefine work and purpose. Genetic engineering may blur the line between human and post-human. In the long term, space travel is not merely mechanical, it is co-evolutionary. Humans and technology will evolve together, defining new forms of civilization adapted to environments we cannot yet fully inhabit. 7. Generational horizons. Consider the concept of a generation ship, a spacecraft traveling for centuries to a distant star. Those aboard may live and die without ever seeing the destination. Knowledge, skills, and culture must be preserved across generations. This scenario magnifies the limits of human travel. Even if propulsion were adequate, survival would depend on social engineering, education, and resilience over centuries. Habitats must be self-sustaining. Communities must endure conflict, disease, and environmental hazards without resupply. In other words, space travel becomes civilization engineering. Reaching the stars is not just a matter of rockets or engines. It is a matter of sustaining humanity itself. 8. The cosmic perspective. When we look outward, the scale is staggering. Earth is a pale blue dot. Mars is a dusty neighbor. Jupiter is a stormy giant. Alpha Centauri is a light year away. Our solar system is but one of billions in the Milky Way. The universe stretches farther still. Space is indifferent. Time is relentless. Distances that dwarf human lifespans are trivial in cosmic terms, yet our curiosity persists. The measure of human progress is not the number of stars we touch, but the expansion of understanding and capability. In a sense, the universe is both horizon and mirror. It challenges us to grow, adapt, and reflect. Every advance in space travel is also a journey inward into human resilience, ingenuity, and identity. 9. Long-term evolutionary implications. If humanity endures, the evolutionary implications are profound. Biologically, humans may diverge into subspecies adapted to different gravitational, atmospheric, or radiative conditions. Culturally, isolated colonies may develop unique languages, rituals, and governance structures. Technologically, integration with AI, cybernetics, and advanced life support may redefine what it means to be human. Psychologically, minds may adapt to long-duration isolation, delayed communication, and new modes of identity. In essence, space travel is not merely a technological challenge. It is a speciation event in slow motion, guided by environment, necessity, and ingenuity. 10. The role of curiosity and imagination. Even today, when humans cannot yet reach Mars without extraordinary risk, or the outer planets without machines, our imagination stretches across the void. Literature, art, simulation, and visionaries project our hopes into interstellar space. Curiosity ensures progress. It drives experiments in orbit, Mars analog missions on Earth, advanced propulsion research, and the ethical frameworks necessary for sustainable colonization. Without curiosity, the question, how far can we go, would never have been asked, let alone answered incrementally. 11. Synthesis, humanity, and the universe. So, what does Section 11 teach us about the ultimate limits of human space travel? 1. Physical limits are defined by life support, propulsion, and biology. Humans are bound to low orbit, near-term lunar missions, and potentially Mars in the near future. 2. Technological limits can extend this reach, but not infinitely. Even advanced propulsion and AI cannot eliminate radiation, isolation, and supply challenges. 3. Evolutionary limits will redefine humanity. Biology, psychology, and culture will adapt or fail. Space demands transformation. 4. Philosophical limits challenge our conception of home, identity, and civilization. Space travel is a mirror of human ambition, risk tolerance, and ethical foresight. The farther we travel, the more human presence becomes a matter of adaptation, foresight, and imagination. Every kilometer beyond Earth tests not just endurance, but civilization itself. 12. Conclusion: the true measure of distance. Distance in space is relative. Measured in kilometers, we are still near home. Measured in time, endurance, and adaptation, the challenge is monumental. Measured in imagination, however, humanity has already traveled to the stars. Space travel is not only about rockets. It is about humanity confronting its own limits, experimenting with endurance, and extending presence through machines, technology, and culture. The universe may be vast, indifferent, and challenging, but curiosity, ingenuity, and courage allow us to stretch farther than our bodies alone permit. In the end, the measure of how far we can travel through space is both literal and symbolic. Literal: low Earth orbit, Moon, future Mars missions. Symbolic: the expansion of human experience, knowledge, and ambition across the void. The stars are distant, but through machines, technology, and imagination, we are already reaching them. And as we adapt, evolve, and innovate, that reach will extend farther still. Space is the ultimate frontier, and humanity has only begun to learn how far it can go. Every civilization that has ever existed has looked up at the night sky and felt a mixture of awe and terror. From the flickering fires of prehistoric camps to the glowing consoles of orbital stations, humans have wondered, what lies beyond? How far can we travel? How far can our bodies, our minds, and our civilizations endure in a universe vast beyond comprehension? The question is deceptively simple, but the answers are layered, spanning physics, biology, technology, psychology, philosophy, and culture. Section 12 is the culmination, the horizon at which we reconcile what humans can do today with what they might accomplish in the distant future. 1. Human presence and the solar system. Today, humanity's current foothold in space is modest but profound. Low Earth orbit serves as a permanent, albeit fragile, home for explorers. The Moon is a temporary destination, a proving ground, a symbol of what we can achieve when ingenuity meets courage. Mars, the near-future goal, represents the first step beyond the cradle, testing endurance, engineering, and society itself. Yet the outer planets, Jupiter, Saturn, Uranus, Neptune, remain tantalizingly out of reach for humans. Only robotic emissaries have ventured there, providing images, data, and glimpses of worlds that may never feel the touch of human feet. And interstellar space, beyond the heliopause, is the domain of machines alone, where human presence is impossible with current lifespans and propulsion technologies. 2. Machines, our cosmic pioneers. If humanity's physical reach is limited, its intellectual reach is not. Robots and probes extend human influence far beyond our biological limitations. Voyager 1 and 2 traverse interstellar space. New Horizons reach Pluto and is heading toward the Kuiper Belt, and countless orbiters map the solar system in meticulous detail. Machines allow us to explore, learn, and even dream, transmitting knowledge across the void that our bodies cannot traverse. They endure radiation, vacuum, and decades of isolation, conditions that would kill any human crew. Yet machines are not autonomous explorers in the philosophical sense. They carry humanity's intent, curiosity, and imagination. Through them, humans have already begun to inhabit the cosmic arena. 3. Physical and technological limits. Distance is only meaningful when paired with physics and technology. Chemical rockets, the workhorses of human spaceflight, permit lunar missions and potential Mars expeditions. Ion engines extend robotic missions to the outer planets. Nuclear and theoretical fusion, or antimatter propulsion, hint at the possibility of human deep space missions. Even with these technologies, the universe imposes immutable limits. Relativity, radiation, energy requirements, and supply constraints define the ultimate speed and reach of any spacecraft. The farther we aim, the more time, energy, and engineering ingenuity are required. Here, human survival is inseparable from technological mastery. Life support, shielding, propulsion, and autonomy are extensions of human biology, bridging the gap between frailty and endurance. 4. The psychological frontier. Human space travel is not just physical, it is profoundly mental. Isolation, confinement, and delayed communication challenge cognition and emotion. Long-duration missions, such as potential Mars voyages, require not only life support, but also strategies for maintaining mental health, social cohesion, and purpose. Generation ships or interstellar colonies magnify these challenges. Humans must adapt to life with delayed feedback, permanent separation from Earth, and a culture defined entirely by the needs of survival. Cognitive evolution may occur, accelerated by environment and technology, reshaping how humans perceive time, community, and identity. 5. Evolutionary horizons. Beyond psychology, evolution itself will respond to the demands of space. Biological, cultural, and technological evolution converge. Biological adaptation. Humans may evolve, naturally or via genetic engineering, to endure altered gravity, radiation, or limited atmospheres. Cultural adaptation. Isolated colonies may develop unique languages, customs, governance, and moral codes suited to survival in extreme environments. Technological adaptation. Life support, AI companions, cybernetic augmentation, and propulsion systems may integrate with human biology to create hybrid humans capable of surviving conditions impossible for current Earth-born humans. Space travel is therefore a laboratory of speciation, not in millions of years, but in centuries or even decades, driven by environment, necessity, and innovation. 6. Interstellar ambition and its challenges. Interstellar space remains a domain of imagination and robotics. Alpha Centauri is 4.37 light-years away. Even optimistic propulsion scenarios project decades or centuries-long travel times. generation ships must sustain not just life, but society for multiple human lifetimes. Cryogenic sleep, hibernation, or post-human consciousness may be required to make interstellar travel feasible. Every challenge magnifies the stakes. Energy, sustaining propulsion over decades, possibly centuries. Supplies, creating fully closed-loop ecosystems. Health, managing radiation, microgravity, and genetic risks. Psychology, maintaining purpose, social cohesion, and sanity across generations. Humanity's current reach is tiny in comparison, yet the human mind already travels farther than the body, contemplating interstellar voyages, designing missions, and dreaming of futures beyond our solar system. 7. Ethics and responsibility. The farther we travel, the more ethical responsibilities multiply. Colonizing planets, moons, or asteroids raises questions. Who decides who travels? What rights do generations aboard generation ships have? How do we balance exploration with respect for potential extraterrestrial ecosystems? Ethics becomes practical survival strategy. Rules that work on Earth may fail in confined habitats or distant colonies. Governance must be autonomous, adaptive, and deeply resilient. Humanity must not only reach space, but thrive responsibly, preserving life and knowledge. 8. Curiosity and imagination as propulsion. Physics and biology define boundaries, but curiosity drives progress. The desire to know, to explore, to extend consciousness beyond Earth has propelled humanity since the first fires burned. Even before humans step on Mars or the outer planets, imagination carries us there. Science fiction, simulations, virtual reality, and robotics extend our reach. Curiosity is a force as real as any rocket engine, propelling the human spirit toward the impossible. 9. Cosmic perspective. Viewed from the void, Earth is a fragile speck. Our solar system is a small neighborhood. Stars are sparse, distances immense. The universe does not bend for ambition. It waits, indifferent and eternal. This perspective is humbling. It reminds us that space is not a resource or a playground. It is a teacher. It challenges patience, ingenuity, and resilience. Every mission, every probe, every human voyage is a negotiation with the scales of time, space, and risk. 10. Humanity's ultimate potential. Even with all limits recognized, humanity's potential is staggering. Within the solar system, we may colonize Mars, orbital habitats, and moons, learning to survive, govern, and adapt. With technological breakthroughs, we may reach the outer planets with humans, extending our presence farther than ever before. Interstellar travel may one day be possible, requiring new biology, AI integration, and societal adaptation. Humanity's journey is therefore not merely about distance, but transformation. The farther we go, the more we must change, biologically, socially, and technologically. 11. Space as mirror and teacher. Every challenge in space reflects humanity's capabilities and limitations. The vacuum, radiation, isolation, and scale act as mirrors. They show us what we can endure, what we must innovate, and what we may one day become. Space is unforgiving, yet it is patient. It allows us to approach slowly, to test, to learn, and to evolve. Our successes, orbit, moon, Mars missions, demonstrate adaptation, courage, and imagination, proving that humans can extend presence far beyond Earth when knowledge and patience are applied. 12. The infinite frontier. Finally, this reminds us that space is infinite in scale, but finite in terms of human understanding, endurance, and ambition at any given time. Every kilometer, every rocket launch, every probe sent into the void is a step outward, a step in knowledge, survival, and aspiration. Humans are limited by biology, technology, and time. Machines extend our reach. Imagination propels us farther than either. Together, these three, body, mind, and machine, define the true frontier of human space travel. The stars are distant, The journey is perilous. Yet the very act of reaching, imagining, and preparing ensures that humanity's presence will extend ever outward. Distance is not simply measured in kilometers. It is measured in endurance, curiosity, courage, and adaptation. And in these terms, humanity has already begun its journey to the infinite. The question that has driven every human civilization, how far can we go, begins in the small circles of orbit, climbs to the moon, stretches to Mars, and extends beyond the solar system. We look to the ultimate horizon, a future where humans are no longer confined to their home star, but traverse the vastness of interstellar space. This section is not about what is easily achievable today. It is about possibility, ambition, and preparation. It is about what humanity may become when our species confronts the full scale of the universe. 1. The interstellar dream. Imagine a journey not of months, but decades or centuries. The nearest stars, Alpha Centauri, Barnard's star, Proxima Centauri, are measured not in kilometers, but in light years. The distances dwarf anything humans have ever traversed. Even traveling at a tenth of the speed of light, a feat of engineering beyond our current capability, such journeys would last decades. Yet the interstellar dream persists. It is fueled not by necessity, but by curiosity, by ambition, and by the awareness that the universe is vast, indifferent, and timeless. Humans have always reached beyond their immediate environment. Interstellar travel is simply the next logical step, one that challenges not just our technology, but our biology, psychology, and society. 2. Generational ships, civilization in transit. For human travel to nearby stars, generation ships may become necessary. These vast, self-sustaining vessels would house multiple generations, who live and die aboard the spacecraft before arrival. A mission spanning centuries requires systems that recycle water, air, and food indefinitely. Every aspect of life, reproduction, education, governance, and culture, must function independently of Earth. Knowledge must be preserved across generations. Social cohesion becomes as critical as propulsion. Conflict, disease, or system failures are existential threats. In this context, the spaceship is more than a vessel. It is a moving civilization, a microcosm of humanity compressed into steel, life support, and community. To survive, humans must adapt in ways previously unimagined. 3. Cryogenic hibernation and life extension. One solution to the temporal problem is cryogenic hibernation. Humans could enter deep sleep for decades or centuries, slowing biological processes and reducing resource consumption. Cryogenics would allow travelers to survive the journey physically and psychologically, while maintaining consciousness over critical decision points. Alternatively, breakthroughs in life extension or biological enhancement may extend human lifespan, enabling interstellar journeys without relying on generational turnover. Either approach fundamentally transforms the human experience, creating a species capable of enduring across the centuries required to traverse even the nearest star systems. 4. Propulsion and energy challenges. Even theoretical interstellar propulsion confronts staggering energy demands. Chemical rockets are wholly insufficient. Nuclear thermal or nuclear fusion propulsion could accelerate spacecraft to a fraction of light speed, but the energy, shielding, and fuel requirements remain extreme. Speculative technologies, antimatter engines, light sails powered by lasers, or exotic physics such as warp drives, offer hope, but remain untested and largely theoretical. Each possibility demands not just engineering, but a revolution in physics and materials science. Every interstellar mission underscores the same truth. Distance is relative, but energy and endurance are absolute. To reach another star, humans must redefine the scale of both. 5. Psychological resilience. Long-duration missions pose profound psychological challenges. Isolation, confinement, and separation from Earth will test the human mind. Generational crews or cryogenic travelers must contend with boredom, monotony, and disconnection from familiar reality. Humans may adapt cognitively. Simulation, virtual reality, AI companionship and cultural rituals can preserve mental health. Emotional resilience will be as critical as life support. Survival in the interstellar void requires not just physical engineering, but psychological engineering. 6. Cultural evolution in space. Societies aboard interstellar ships or distant colonies will evolve uniquely. Isolated from Earth, language, governance, art, and ethics may diverge rapidly. Mars-born humans may develop different norms than Earth-born humans. Generation ships may produce entirely distinct cultures adapted to life in transit. Cultural evolution becomes accelerated in space. Every challenge, scarcity, isolation, decision-making under risk shapes human behavior. The farther we travel, the more civilization itself must adapt. 7. Ethical considerations. Expanding humanity beyond Earth raises profound ethical questions. What rights do travelers and future generations aboard generation ships hold? How do we preserve life and ecosystems on distant worlds? Who decides the destiny of humans venturing into the stars? Ethics in space is inseparable from survival. Every rule, governance structure, and cultural norm must sustain not only life, but society and knowledge across generations. Human expansion becomes a test of moral, as well as technical, ingenuity. 8. Evolutionary implications. Space travel is a driver of human evolution, biological adaptation. Humans may genetically adapt to altered gravity, radiation, or closed habitats. Technological symbiosis. Integration with AI, cybernetics, or life support systems may redefine what it means to be human. Psychological transformation. Minds may evolve to handle extreme isolation and delayed feedback. The universe acts as a selective environment. Humans in space are not just explorers, they are evolving, potentially becoming a post-human species, adapted to survival far beyond Earth. 9. Communication across the void. Interstellar distances make communication with Earth slow, sometimes impossible. A message to Alpha Centauri takes 4.37 years at light speed. Decisions cannot rely on Earth-based guidance. Travelers must be autonomous, capable of managing crises, innovation, and cultural continuity independently. This independence transforms the nature of human exploration. Space travel becomes less about Earth-centric missions and more about self-sustaining human presence across the cosmos. 10. Machines as cosmic allies. Even in the interstellar era, machines remain essential. Robots can precede humans, surveying planets, testing habitats, and mapping hazards. AI companions can assist human travelers in navigation, life support management, and problem solving. Machines extend human reach, enhance survival, and preserve knowledge. They allow humans to project influence far beyond biological limits, bridging the gap between desire and capability. 11. The role of curiosity. At the heart of interstellar ambition lies curiosity. It propels humans to endure danger, solve impossible problems, and extend presence across unimaginable distances. Curiosity is the force that transforms risk into exploration, imagination into reality, and the impossible into milestones of achievement. Without curiosity, even the most advanced technology and resilient biology would remain idle. Curiosity ensures that humans, individually, collectively, and across generations, continue to push boundaries. 12. Cosmic perspective. Viewed from a distance, Earth is fragile. The solar system is small. Stars are isolated. The galaxy is vast. Space is indifferent to life, civilization, or ambition. Yet the very act of reaching, measuring, and imagining imposes meaning onto the void. Humanity's cosmic journey is both literal and symbolic, a physical expansion and an intellectual, cultural, and philosophical adventure. Every probe, habitat, or interstellar concept is proof that intelligence can persist, adapt, and endure. 13. The infinite horizon. This reminds us that the universe is effectively infinite for any single human lifespan. Distances dwarf our bodies and lifetimes. Time stretches across centuries and millennia. Yet humanity's reach grows, powered by technology, culture, imagination, and resilience. Even if we never personally travel to distant stars, humanity's presence, through machines, knowledge, and legacy, already stretches far beyond Earth. The infinite horizon is not a limit, but a canvas upon which human ingenuity paints its future. 14. Synthesis. Humanity, technology, and the stars. Interstellar travel, as envisioned in this section, is more than a technical problem. It is a convergence of biology, psychology, society, ethics, and imagination. To survive the void, humans must adapt biologically and technologically, maintain social cohesion and cultural continuity, navigate psychological and ethical challenges, harness machines as allies, not replacements, sustain curiosity, resilience, and purpose across generations. The journey is not just outward, it is inward, into the nature of humanity itself. 15. The final reflection. How far can we travel through space? The answer depends on perspective. Today, low Earth orbit, lunar missions, and near-future Mars exploration define human reach. Machines extend human presence to the outer planets, heliopause, and interstellar space. Centuries ahead, generation ships, cryogenic sleep, AI integration, and human evolution may allow distant stars to be reached. Distance is not just physical. It is measured in adaptation, endurance, and imagination. The universe is vast, but human curiosity and resilience make even the void navigable, at least conceptually, if not yet physically. 16. Conclusion. Humanity's place in the cosmos. Space is the ultimate frontier, infinite, indifferent, and awe-inspiring. Humanity's journey is only beginning. Rockets, probes, habitats, and AI companions extend our reach. Biology and psychology define the limits of endurance. Culture, ethics, and imagination shape how we survive and thrive. Ultimately, the measure of human space travel is not in kilometers alone. It is in vision, adaptability, and ambition. Even if the stars remain distant, humanity has already begun to inhabit the cosmos through intellect, machines, and foresight. The question, how far can we travel, transforms into a deeper question. How far can we imagine, endure, and evolve? And in this, the answer is already infinite.